If you look closely at a fractal or a quasicrystal, it is easy to get lost. You are looking at a mesmerizing mathematical phenomenon, an endlessly repeating geometry that creates infinite, unpredictable complexity from a few simple rules. For 4 years, a research project known as FfeD explored a very specific hypothesis. What if we could take that infinite visual chaos and use it as a source of secret entropy to secure data? This idea evolved into quasicrystal lattice cryptography, or QLC. The early ambition was to transform sensitive information into these non-periodic lattice structures, making the data itself an inseparable part of the geometry. But a structure that looks complex to the human eye behaves very differently when tested against the strict, unforgiving requirements of a cryptographic primitive. Human intuition naturally assumes that if a pattern is chaotic and visually dense, it must be mathematically impenetrable. In cybersecurity, relying on that intuition is a fatal flaw. The problem begins the moment you take a pristine, theoretical equation off a chalkboard and force an actual computer processor to calculate it. This animated diagram illustrates the floating point problem. Because computer hardware has limited memory, it has to round off infinite decimals. Depending on the processor architecture, 2 identical machines running the exact same equation can generate a slightly different numerical string. Those tiny rounding differences compound. Within milliseconds, a microscopic decimal variation turns into an avalanche of mismatches. You can draw the same shape on a Mac and a PC, but you cannot generate the exact same mathematical sequence on both. To encrypt and then successfully decrypt a file, you need absolute bit-for-bit parity. This means numerical sensitivity, the very thing that makes fractals so chaotic, is actually a liability. It makes the results impossible to reproduce across different systems. When tested against strict, standardized benchmarks for diffusion and randomness, the beautiful, intricate geometric construction completely falls apart. But discovering exactly how and why a complex pattern fails to provide security is highly valuable. For a student, that failure is a far better teacher than a system that merely looks complex. This friction between theory and hardware led to a change in the project structure, the creation of the multi-recipient orbe. In this design, the role of ensuring confidentiality and integrity was handed over to standardized, proven primitives like ChaCha20 Poly 1305. The entropy is handled by recognized algorithms, not visual patterns. But the research into Apollonian geometry wasn't discarded. It was repurposed as the outer shell of the data envelope. This outer layer now acts strictly as public context. It serves as a verifiable map of the data's context and provenance, tracking its journey without being responsible for its secret key. This establishes a necessary boundary in system design. You separate the verified mechanisms that defend the data from the experimental visualizations used to describe it. To enforce that boundary in the classroom, the project introduced Vigil. Think of Vigil as a pedagogical coordinator that stands guard while students interact with the orbe. Vigil does not use generative AI to guess if a system is secure. It relies entirely on a deterministic engine to verify the math against known security standards. This creates an adversarial learning environment. Students attempt to build their own geometric permutations, and then Vigil forces them to perform a strict avalanche test to see if their math actually obscures the data. The output is uncompromising. Vigil issues a binary accept, suspend, or reject based purely on whether the student can provide a mathematical proof of their claims. The entire platform operates as a digital demolition lab. It is a space where an intuition about geometry becomes a testable hypothesis, and a failure becomes a negative proof. The goal of this curriculum is to build the skepticism required to distinguish a complex image from a verified proof. It trains the student to value evidence over the appearance of security.